So I know it's been a long time since I've last done a video, but I like to get back into it. And so today we're going to be doing a passage on electricity and magnetism. That's a section that a lot of my students have trouble with. And what I want to illustrate here in this example is that the concepts or the knowledge that you're expected to demonstrate on the exam is actually pretty superficial. You don't have to know in detail how these things work. It's more so how able are you to read the passage, decipher what they're asking you, and to demonstrate that knowledge. But it's you don't have to have a complex understanding of these things. It's more, can you perform good reading comprehension and then remember some superficial details. So let's just get right into it. So students constructed the electrical circuit shown below to study capacitors. A battery with a voltage of 10 volts is connected through a switch to a capacitor and a 500 ohm resistor. So if they didn't give you this figure, you would probably be better off actually drawing it than just thinking about it in your head. Or if you don't draw it, visualize these things as you read them along. It's really important to be visualizing everything you're reading in these passages. It'll keep you more engaged and it'll sort things out in your head for you. The capacitor is constructed from two flat metal plates, each with a surface area of 5 times 10 to the minus 5 meters squared. The plates are separated by a 1 times 10 to the minus 3 meters, and the space between the plates is a vacuum, so you don't have to worry about the dielectric stuff. The connecting wires have no resistance. After the switch is closed and the capacitor is fully charged, a particle with a charge of 8 times 10 to the minus 19 coulombs and a speed of 1 meter per second is injected midway between the capacitor plates. Okay, so there's kind of a lot of things going on here. So basically it's telling you that we have a circuit. In the circuit, it's a very simple circuit. We have a capacitor right here that's charged via this 10 volt battery. There's some internal resistance in the circuit, which is good. So you don't need to have knowledge. So basically what's going on, this is called an RC circuit. But for the MCAT, you don't need to know exactly how this works. You don't need to know like the timing of the charging and discharging, things like that. But just know that there's a battery involved, there's a resistance, and there's going to be some amount of time that it'll take for the capacitor to get charged, and you know that, right? So this is the negative lead of the battery. You're going to have negative charges flowing. The electrons are going to be flowing in this direction, and they're going to be lining up on this plate, and that's going to give this a negative charge, and it's going to have a positive charge. And because the electrons are moving in this direction, you're going to have the current moving in this direction. Okay? And so once the capacitor is charged, we're going to put a particle midway between the capacitor plates. And as you know, when you charge a capacitor, you form an electric field. And so probably when we put in that electron in that electric field, it's going to move in some direction. We can guess that it's going to move towards this bottom plate right here because we know that this top plate is going to be negatively charged, and that negative charge is going to repel that negatively charged electron. All right. So now that we have a good understanding of what's going on in the passage, we can move on to the questions. And just as an aside, I know there are a lot of weird strategies going on, that people hear about. Some people say to read the questions first and then go back to the passage, or skip the passage, go to the questions, then come back. My philosophy is, and that of basically all my tutors, is that I think you should have a very good understanding, or at least the best understanding you could possibly have in the period of time that you're reading of the passage. And that way you can move on to the questions confidently, and you know what the general idea is, and then you can, if you need to, you know where to find things if you need to go back to the passage, and so on and so forth. So I think it's a good idea to know what's going on in the passage first, and then move on to the questions. So which of the following graphs best illustrates how charge accumulates on the plates of the capacitor after the switch is closed? So the first thing you want to do when you get graphical questions is to look at the axes. So on the y-axis we have charge, and on the x-axis we have time. As we know, is the capacitor is being charged up, right? It's getting charged. So we expect that over a period of time, the charge should increase on the capacitor, okay? So any of the graphs that show charge decreasing or not increasing are out of the question, right? So A is going to be out. So now we're left with B, C, and D. They all show increasing charges. Okay, so then the next important fact that you need to know is how capacitors work. So if you knew how RC circuits worked, you'd be able to get this answer very quickly. But let's say that you don't know how they work, and you don't need to know how they work for the exam. You should know that the capacitors can hold a certain maximum amount of charge. Okay, after a certain point, doesn't matter how long you keep it plugged in, doesn't matter how long it's connected to a battery, it cannot hold more charge. And that's essentially what the capacitance is. That's how you calculate the capacitance. And there are equations that will tell you how much charge a certain capacitor can hold given a certain battery. But we should know that at a certain point, the amount of charge that can be held while it's connected to this battery is going to reach a constant. Okay? And so we're going to look for the graph that shows some slowing down. Okay, so after some point of charging, there needs to be some slowing down and then some flattening. Okay, so if we look at C and D, C is a linear function, which means that after it just the amount of charge on the capacitor increases linearly with time, and it doesn't show any signs of slowing down. Okay, it's just going to increase at that rate, which doesn't make sense. Okay, and D is an even more extreme form of C, where not only does the charge increase over time without bound, it's increasing exponentially, which would be impossible, right? The capacitor has a certain physical parameters that would hinder it from growing exponentially, of course, right? So it has a certain area that's defined over here. So the only one that would make sense is B, because B is kind of showing a more logarithmic function, where it looks like after a certain amount of time that that slope is slowly decreasing, and eventually we'd hope for it to stop and flatten out, and that would be the capacitance of the capacitor. So then B would be the correct answer. Okay. Number 7. If the speed of the charged particle described in the passage is increased by a factor of 2, the electric force on the particle will what? So when you read this question, especially in physics, you want to be thinking in terms of equations. Okay? And even especially when we're doing electricity and magnetism, because these concepts are really not that intuitive. So mechanics, maybe you don't have to think entirely in equations, but for E&M, I don't know how you conceptually know how these things work. So what's in question here is how we determine the electric force. And in this very simple setup, we know that when we put that particle in between the plates of the capacitor, it's going to be affected by some electric field. Okay, so you got to go back into your head and think, what equations do we have for electric field and force? And we know of one very simple equation, F is equal to QE. Okay, so the only terms in that equation are one, Q, which is the charge of the particle, which is the elementary charge of an electron, and E, the strength of the magnetic field. Of the electric field. So those are the only two terms that go into the equation. So the speed is not a term that goes in, and then we can logically say that the speed does not have any effect at all. So B would be the correct answer. So what they're probably trying to do with this question is confuse you with magnetic fields. So there is an equation for how charged particles will behave in a magnetic field, and that's F is equal to QV cross B. And in that equation, the velocity actually has a direct impact on the force. But we're only dealing with electric fields here. We just have a circuit. There's no mention of a magnetic field, a B field, or coils, or any currents creating a magnetic field. So we have a very simple setup: capacitor, electric field. F is equal to QE. There's no V in that equation, so we're going to say it remains the same. Number 8. Making which of the following changes to a circuit element will increase the capacitance of the capacitor described in the passage? Again, so maybe for capacitance there could be some intuition as to how you would increase it, but for the most part I want you to think in terms of equations. So you got to go back into your head and think of the equation of capacitance, and if you remember, it's C is equal to epsilon naught A over D. So epsilon naught is some constant. A is the surface area of the plates. So that's a number that's given over here. And d is the distance between the separation between the plates. So essentially, what that equation tells you is that if you increase the area, you're going to increase the capacitance, and if you decrease the distance between the plates, you're also going to increase the capacitance, right? So A says replacing the 500 ohm resistor with that has nothing to do with the capacitor itself. Okay, that's not going to change the capacitance. It might change the amount of charge you can store on it, but it won't change the amount of charge that could be stored. Okay, so B says replacing a 10-volt battery with 20. Again, that has nothing to do with the capacitor. C says increasing the separation of the capacitor plates, and D says increasing the area of the capacitor plates. So C and D have to do with the capacitor, which is good. So remember in our equation epsilon naught A over D, if we increase D, because it's an inverse relationship, we should be decreasing C. So that means that answer choice C is incorrect, right? We want to decrease the separation to increase the capacitance. And so we get to D by process of elimination. Let's just see if it's correct. We increase the area of the capacitor plates. We know that C, the capacitance, and A, the area, have a direct relationship. So if we increase A, we should increase C. And that makes answer choice D the correct answer. All right, number 9. A charged particle with a mass m and a charge q is injected midway between the plates of a capacitor that has a uniform electric field of E. What is the acceleration of this particle due to the electric field? Okay. So we know that back to 2 questions ago, if we put a charged particle in an electric field, that particle should feel a force. Okay? And as we know from Newton's laws, that if a particle experiences a force, then it should accelerate. Okay, it should experience an acceleration as well, so long as it has a mass. Okay, and that's Newton's second law, F equals ma. So we can get F through the equation F equals QE, and we also know that F is equal to ma. So that means that we are left with QE is equal to ma, and all I have to do is solve for A, right? So QE is equal to ma. We divide both sides by m, so we get A is equal to EQ over F is equal to QE. Yeah, EQ over M. That should be answer choice A. All right. Another capacitor identical to the original is added in series to the circuit described in the passage. Compared to the original circuit, the equivalent capacitance of the new circuit is what? Okay. So now we have to go back to, again, our equations. And we have to remember how equivalent capacitance is calculated given putting them in series. Okay. So remember, in series, it's as if we're increasing the distance, right? If we're adding another capacitor, it's like we're increasing the distance of one capacitor, and we know that decreases the capacitance. So now we know that we have to go to the equation with the inverse relationship. So that'd be the 1 over equation. So that means that 1 over CEQ is equal to 1 over C1 plus 1 over C2. So if we add another capacitor that's identical to the original, we should be decreasing the capacitance for sure. Okay, so that's what happens when you put them in series. So you don't even have to plug in the equations at all. Okay, we're going to look for the answer choice that says the capacitance decreases somehow, and B, C, and D don't say that, and A is the only one that actually has a decreasing capacitance, so that's the one we're going to go with. Okay, last one. Which of the following best describes the motion of a negatively charged particle after it has been injected between the plates of a charged parallel plate capacitor? Note, assume the area between the plates is a vacuum. Okay, so this is a really simple question. Sorry. So all you have to know is how do charges interact with each other, and we know that like charges repel and opposite charges attract. So an electron that's negatively charged is going to be repelled by the negative lead. So it's going to move with the okay, so we know that whatever whatever choices have it moving towards a negative plate would not make any sense, right? So that would be B, and D would be out. So now we're left with A and C, and the question is, does it accelerate or does it move with a constant speed? And we know from question 9, because it's experiencing a net force, it will also experience an acceleration. Okay, so it's almost as if it's falling, like, a ball is falling towards the earth. We have this electron is going to be falling towards the positive plate, and that would be answer choice C. All right, so again, not too bad, right? The main key is to try to think of the equations and the minor concepts that are involved with what you had learned in your content review, and try to link them to the questions and the passages.